Welcome, everybody. So the last thing that we're going to talk about in Physics 213 this term is how inductors work when I put them in a circuit. So as we talked about earlier this week, inductors are really just a solenoid, a big coil of wire that I toss into a circuit. We know from Faraday's law that we can relate the voltage across an inductor, the change in the current through that inductor. I've got an equation for that right here. And we're going to try this out in a circuit. So let's go ahead and launch right into it. The circuit, which I already had you think about over in your Get Ready activity, is a pretty simple one. I've got an initially charged capacitor over on the left, and I have an inductor over on the right, and I'm going to close the switch here. Now, when we talked about RC circuits a few weeks ago, we noticed that if I put a capacitor with a resistor, when I close the switch, what will happen is the capacitor will discharge, right? All the charge will start flowing through the circuit as current, and eventually there won't be any charge on the capacitor. And we're going to try to see if the same thing happens here or if we get slightly different behavior. One thing to note for this particular problem is that we're treating both the capacitor and the inductor as ideal, perfect, non-resistive elements. So there's no resistance in this particular circuit. So the first thing that I had you think about is when I close the switch, the initial current is going to be 0. I wanted you to give a physical reason for why this is going to happen. And the secret to understanding inductors is actually to flash back over here to the voltage across the inductor. The voltage has to be proportional to the derivative of the current. One thing that means is I can't ever have an infinite voltage across the circuit, which means that the current can never be discontinuous, right? If I ever have the current, if I were graphing the current, if it ever goes along and it's like happily kind of rolling along and then suddenly it jumps down here, that's an infinite jump in the current, right? That's an infinite derivative. And I'm not allowed to have that. So the current through the inductor is going to have to be continuous and kind of smooth. So when I look at the circuit, the reason the current has to be 0 when I close the switch is because it was 0 before I closed the switch, and it needs to be continuous. Once I know that, I can kind of think about what's going to happen as a function of time here. And I'm going to use some qualitative reasoning to do it. So I know the current needs to start 0, but I also know that the voltage across the inductor is not going to be 0 initially, because I can do a Kirchhoff's loop rule and say that whatever the voltage across the capacitor is has to be equal to the voltage across the inductor once I close that switch. And that means that I have to have a non-zero derivative in the current, right? So it starts at 0, but it starts with some non-zero derivative. So something like that. However, as soon as some current starts flowing through this circuit, the capacitor starts discharging. And that means that the voltage over the capacitor decreases. And Kirchhoff's loop rule says the voltage over the capacitor decreases, and the inductor is the only other thing in the circuit. And the voltage across the inductor also decreases. And again, the voltage across the inductor looks like a derivative. So this thing is going to decrease its derivative again and again and again until it gets flat. Now, a really interesting thing happens. Oh, and I should put some labels on my axes here. This is time, and I'm graphing the current through the circuit. So a really, really interesting thing happens when I increase the current here, which is I get to this flat value, and the derivative is 0, right? Which means there's no voltage over the inductor, which means there's no voltage over the capacitor. It means there's no charge on the capacitor, but there's still current flowing through the circuit, right? There's a whole bunch of current going this way, even though there's no charge left on the capacitor. And we just argued a few minutes ago that the inductor can't just say, okay, well, I'm done, and go to 0 and be like no more current. It has to decrease smoothly. And so this current's going to start coming back down. But as it does that, you now have a slope to that current, which means you've got voltage across the inductor, means I've got voltage across the capacitor. And so what happens here is you get a flip of the charge on the capacitor, where it used to be all the positives up here, all the negatives down here. Now the current is going to start building up positives on the bottom and negatives on the top until I get to this kind of equilibrium position where the capacitor is supercharged and the inductor says, okay, I no longer need to have any current flowing through. And this sort of thing is going to cycle. It's going to go back and forth. And so that's kind of our prediction for what is going to happen here. We're going to see if we can extract that behavior using the mathematical tools that we got. So those tools say that, again, I can say Kirchhoff's laws tell me that Q over C is equal to minus L dt. That's just Kirchhoff's loop rule. I know that the current I is the derivative of the charge with respect to time. So then I have a differential equation that looks like Q equals a constant, a negative constant, times the second derivative of Q. This isn't a differential equations course, so I look to mathematician Paul, who says this is a second order differential equation with constant coefficients or some other nonsense like that. But he knows how to solve this. And it turns out that this is actually the harmonic oscillator equation. We solved it last term in 212 when we were doing oscillations. The solution is that the charge and the current, which is the derivative of the charge, oscillates back and forth like a cosine function with angular frequency 1 over the square root of LC. And we already know how to handle this exactly, right? We can graph this. We know what cosines and sines look like. We get exactly this behavior that I just described, where the current starts out small, gets larger, gets smaller, gets negative, gets positive, and it just goes back and forth, right? So this is the overall behavior of an LC circuit, that has just an inductor and a capacitor.